Ok, da questo momento allora, presento il intero. Allora, da questo momento dovreste vedere il desktop. Quindi adesso andiamo qui e cominciamo la lezione con la parte di PowerPoint. Okay. Oggi useremo la lavagna soltanto poi diciamo nell'ultima parte della lezione. Allora, dunque fatemi fare un attimino un riassunto di quello che abbiamo visto ieri. Quindi ieri abbiamo sviluppato il formalismo dell'elettrodinamica quantistica basandoci sull'approccio perturbativo che è stato diciamo, proposto tra gli altri da Feynman, a cui si deve anche il merito di aver inventato questi metodi grafici che sono i diagrammi di Feynman, che come abbiamo visto non sono soltanto delle rappresentazioni grafiche dei processi fisici, quindi dei decadimenti o delle interazioni, ma ogni pezzo di quel diagramma, okay, ogni simbolo che compare nel diagramma in realtà corrisponde a un pezzo della nostra matrice di transizione, okay, quindi la nostra transition probability amplitude, che poi a sua volta andrà inserita nell'espressione finale della sezione d'urto che abbiamo ottenuto a partire dal regolatore di Fermi, e quindi tutto questo meccanismo ci consente di fare calcoli, come vedremo oggi anche di altissima precisione, su processi appunto regolati dall'interazione elettromagnetica. In particolare abbiamo sviluppato il formalismo su come ricavare l'elemento di matrice per quanto riguarda lo scattering Moller, che è diciamo, il processo più semplice in cui D è lo scattering elettrone-elettrone, quindi elettrone-elettrone che va in elettrone-elettrone. Lo abbiamo fatto in due modi, se vi ricordate, quindi basandoci su principi primi, quindi partendo dall'equazione di Dirac per un elettrone in un campo elettromagnetico e applicando appunto l'approccio perturbativo. Questo diciamo, ci ha impiegato un po' di tempo, però diciamo, abbiamo capito anche più in dettaglio la fisica che ci sta dietro, e poi abbiamo ripetuto invece il calcolo utilizzando invece le regole di Feynman, le Feynman Rules, quindi le regole appunto che consentono semplicemente di tradurre in un rapporto 1 a 1 i vari pezzi che entrano nel diagramma di Feynman in pezzi che entrano poi nell'elemento di matrice. E quindi abbiamo ricalcolato l'elemento di matrice per lo scattering Moller, in particolare meno I, MFI, se vi ricordate, in cui si evidenziano i tre pezzi fondamentali, quindi abbiamo la corrente nel vertice superiore, la corrente nel vertice inferiore, in cui a sua volta si identificano all'interno i vertex factor, okay, fattore di vertice, e poi il propagatore del fotone in mezzo, espresso in termini del G mu, okay, della metrica. Allora, tutto quello che abbiamo visto, e poi abbiamo visto anche tutta una serie di altri processi, ok? Abbiamo visto il processo di più e meno, che va in più o meno, e lì abbiamo appunto visto come la conservazione dell'elicità nei processi elettromagnetici in realtà consente di scartare, è proprio la natura che scarta tutta una serie di combinazioni di elicità tra particelle iniziali e particelle finali, quindi su 16 totali combinazioni soltanto 4 sopravvivono, e poi abbiamo utilizzato queste 4 per calcolarci alla fine la sezione d'urto e confrontarla con i dati sperimentali. E poi abbiamo visto anche una carrellata di altri processi come la produzione di coppie, il Compton, lo scattering Babba, che è lo scattering elettrone-positrone. Lì, in questa volta, senza andare nel dettaglio, vi ho mostrato sostanzialmente le idee principali, quali sono i diagrammi a primo ordine che contribuiscono e come, diciamo, e qual è poi l'espressione, se volete, finale dell'elemento di matrice, come si assemblano i contributi dei vari pezzi e i termini di interferenza. Ripeto, qui in questi altri processi non siamo andati nel dettaglio, il dettaglio del calcolo è piuttosto laborioso, non è una cosa che mi interessa particolarmente, e per chi di voi è curioso la trovate sviluppati sul testo Alzen-Martin, che è uno di quelli consigliati. Bene, partiamo adesso sulla parte nuova di oggi, quindi adesso passo in inglese. So far we have considered only first order diagrams, okay? Quindi i diagrammi di livello più basso. However, for an accurate calculation of the cross-section for a given electromagnetic process, one should, in principle, include all infinite higher order diagrams. So the full transition amplitude of each elementary physical process is given by, in fact, an infinite series of Feynman diagrams with the same initial and final state particles. It becomes more and more complex as the order of the expansion increases. So here you see an example. So the first diagram that you see on the left is the first order one. So for instance, one that the Moller scattering, for instance, what we studied yesterday. Then we have 1, 2, 3, 4, 5 diagrams at the second order, okay? Where you see that the number of vertices is not anymore just 2, but you have 4 vertices. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, etc. Okay, and then you can even go further. Here you can have, of course, diagrams with with a higher number of vertices, 5, 6, 7, 8. In principle, infinite. Okay, so this is in principle an infinite expansion. And the total amplitude at a given order, suppose you want to stop your calculation at the third order, okay, is obtained by adding up all the amplitudes corresponding to all the diagrams that can be drawn up to that order. Okay. Now, what is the meaning of this expansion? So this series reflects the expansion of the transition amplitude in powers of a small parameter, and this is in fact the essence of the perturbative approach. Okay. And the order of the expansion reflects the number of vertices, as I was mentioning before, and each vertex contributes as square root of alpha, where alpha is the fine structure constant, as we will see in a moment. Okay. So essentially, we are using a perturbative approach. This is the Feynman approach. Okay. So we are making an expansion of our theory in terms of a small parameter that, in the case of electromagnetic interaction, is alpha. Okay, the fine structure constant. And then we have infinite terms here, okay, which becomes more and more complex as soon as you go ahead with the expansion. So we have the leading order term, the one that we discussed yesterday, where you just have two vertices. Each vertex contributes square root of alpha. So here you just have, so this probability amplitude is proportional to alpha. And so the probability will be proportional to alpha squared. Then you have, in this case, here you see the case with 4 vertices, the one that I showed in the previous slide. Okay, so now the probability amplitude goes with alpha squared, and so the probability goes with alpha to the 4th power, etc. Now, what is the value of alpha? Okay, alpha, as we've seen many times, is the fine structure constant. We can call alpha electromagnetic or just alpha. And you see here how to express it in different unit systems, so international system, TGS, and natural units. In all cases, you see that alpha is essentially proportional to the squared of the electron charge. Okay, and you see the value here. Okay, the value, let's say at low energy, is order of 1 divided by 137. So it's a very small number. It's a relatively small number, and so it is perfectly suitable to be used as a small parameter in a power expansion. And this is indeed how this power expansion is performed. Of course, if this value would be larger, so order of 1, as it is the case of QCD, as we will see, then of course you cannot use perturbative methods, or at least you cannot use this parameter as the small parameter for the perturbation. Okay. Now, the name fine structure content, as you know already from atomic physics, derives from the fact that it determines the size of the spin-orbit splitting in atomic spectra, the fine structure of the atomic spectra. But of course, more fundamentally, for what concerns us, alpha represents the coupling constant that specifies the strength of the interaction between charged particles and photons. Okay. Now, since alpha is a very small number, so much smaller than 1, the series, okay, actually converges very rapidly. And fortunately, only few lower order processes will contribute to a non-negligible level to the cross-section. Okay. The dominant contribution, of course, to the cross-section or the decay rate, whatever, it corresponds to the leading order diagrams, the one that we studied yesterday, okay, which are also known as the tree-level. So leading order diagrams or tree-level is the same thing. Then, of course, one want to make the calculation more accurate, so you want to add higher orders, and each subsequent order in the expansion corresponds to additional vertices in the diagram, each vertex contributing to square root of alpha. And so the probability will be smaller by a factor of alpha for each additional vertex. Okay. So that means that your series converges very rapidly. So you don't, fortunately, have to compute infinite diagrams. Okay. And if you stop yourself already at the leading order, okay, you're making a quite precise prediction. Okay. So the calculation in QED, if you stop already at the tree level, are already precise at 1% level. If you want to get 1 per mil or even less, you have to add the second order, the third order, maybe also the fourth order, but then it is not worth to include more diagrams because the calculation becomes complex and the contribution is negligible. Okay, and all these thanks to the fact that the alpha parameter is a small parameter. Okay, so the series converges very rapidly. There is another comment here, something that we already saw yesterday. So as we have seen yesterday in the simple case of the molar and the bubble scattering, a minus sign must be included between diagrams that differ only by the interchange of two incoming or outgoing fermions or antifermions, or of an incoming fermion and an outgoing antifermion, or vice versa. And all these essentially arise from the anti-symmetrization imposed by the Fermi statistics. Okay, so when you have undistinguishable fermions, you have to add this minus sign if you want to make everything consistent when you are adding diagrams with the same final states. Now, so, okay, hope it is clear now that if you want to make an accurate QED calculation, okay, you have to include not only the leading order terms, but also some of the higher orders, the second order, the third order, essentially, okay. All higher orders becomes very complicated to calculate. You see how many diagrams already we have here at the second order. So imagine how many we have at the 7th order, 8th order, 10th orders. And, but their contribution will be essentially extremely negligible, okay. So the situation is rather simple in quantum electrodynamics. However, there is a complication. Okay, we are now in slide 4. A serious complication, actually. And this arises when dealing with the higher order diagrams. And in fact, it turns out that the theory is intrinsically divergent at large momenta. We call this ultraviolet divergence. And obviously, a divergent theory cannot describe a physical process. So something must be wrong or must be corrected to the theory. And so until a solution was found, that took quite some years, the full reliability of QED was put under serious doubts by the physics community. So let's see now what is the problem here. Let's first, okay, discuss what is the solution, then we focus on the problem. So the solution of this ultraviolet divergence, okay, in higher order diagrams in QED, is known as renormalization, something that we already mentioned before when we introduced the gauge theories. Now, the renormalization was first proposed in a covariant formulation by Schwingber, Tomonaga, and Feynman. However, the approach does not work for the strong interaction and the weak interaction, but only for the electromagnetic interaction. Then a more general approach was introduced later by Toft, who rigorously demonstrate that something very complicated, okay? So he demonstrated that a spontaneously broken Young-Mills theory, such as the standard model, if you want, the electroweak theory, is by construction renormalizable. And this new approach could be successfully applied also to the strong interaction and the weak interaction, and constitute, in fact, the basis of the modern gauge theory, so the standard model of particle physics. However, the proof of this demonstration is extremely complicated. He got a Nobel Prize for this, and it goes, of course, well beyond the scope of our course. So we will not go through this, of course, but rather I will, in the next slide, I will just show you a simple case of divergence in QED, and this will help me to draw some essential idea about the renormalization, okay? So in the following, I will show you something, let's say, partially qualitative, okay? But just to give you the idea of what the normalization is and how it essentially makes the basis of gauge theories. So let's see how the problem of these ultraviolet divergences arises in QED. So the simplest higher order correction to the photon propagator is the so-called vacuum polarization graph, where the virtual photon, okay, suppose we have an electron that interacts with an atomic nucleus of charge Ze. Of course, the interaction comes through the exchange of a virtual photon. At first order, leading order, you just have a virtual photon here. But then you can also have this second order graph, where your virtual photon splits into an electron-positron pair, which then eventually recombine to a photon and then interact with the nucleus. Okay. So this is for a higher order because you have two more vertices here. Okay. So you have the one here, the one there, and two more vertices. And you see also at each vertex the contribution to the vertex factor, which is also here depicted. Okay. So we have four vertices. Now let's see what is the problem here. This loop diagram, loop because we have a loop inside, okay, requires an integration over the E plus E minus propagator over the loop for momentum P. So the for momentum that runs into this loop here. And also an additional extra -1 to the n factor for each fermion loop. In this case, we have just one loop, so n is equal to 1, so just a minus sign here. Why do we have to integrate this electron-positron propagator? And the reason is the following. And actually constitutes a specific Feynman rule for loop diagrams. Okay, the point is that although the form momentum, of course, is conserved at each vertex, the momentum P that circulates around the loop is completely unconstrained. This is all virtual here. Okay, so in principle, it can take any value from 0 to plus infinity. And since it is not observable, we have to integrate over all possible values. And so this is the reason why we have to integrate from 0 to infinity of the form momentum circulating in this loop. Okay. So now the matrix element for this process would look like this. So we have the current at the upper vertex, as we showed yesterday. So this is the adjoint spinor for the final state particle, the outcoming electron here. Then we have the vertex factor, I, E, gamma mu, and then we have the spinor for the initial state. Okay, as we discussed yesterday. Then we have to add this minus sign that comes from the Fermi statistic. That comes from the theory. Okay, from here, where n is equal to 1 because we just have one loop in this case. Then we have the electron-positron propagator. Okay, that we have to integrate over the momentum from 0 to infinity. Then we have the other photon propagator here, and then finally we have the current or just the charge in this case because we don't have a current here. We can also represent as another electron positron or whatever here. In this case, the example is based on just a simple atomic nuclei. So this is how the matrix element would look like if you take into account all these contributions here, and you remember that you have to integrate over the momentum the electron-positron propagator. So far, so good. Now, the problem is that this integral diverges logarithmically with high momentum. So as soon as we go to momentum that goes to infinity, we get a logarithmic divergence here. And if this term diverges, the full matrix element diverges, and the cross-section diverges, and of course we get something that is non-physical. So this was the problem at the origin, okay? And let's now see how it is solved by the renormalization procedure, okay? So a solution can be obtained by introducing a so-called cutoff parameter m squared that replaces the infinity as the upper limit of the integration. So as a first step, you substitute the infinity with something like with the cutoff parameter m squared. But of course, this is not a trick because you recover your divergence in the limit where m squared goes to infinity. Okay. Now, once you change this in your integral limits, okay, you can solve the integral, and this is the solution. Okay, where you still have your divergent cutoff parameter inside the logarithm. Okay, so this quantity is still logarithmically divergent. However, we don't have any more explicitly the infinite symbol, but just some cutoff parameter. Now, we put this into the matrix element that we have seen before, and then after some algebra that, if you're curious, you can find in the Alzheimer-Martin. It's quite complicated. You will find this expression for the matrix element. Okay, so again, we have the current here. We have something that reminds us the combination of the photon, and then all the rest is here, where again, the divergence is still present. Okay, is still encoded in this cutoff parameter m squared that one should at the end put up to infinity. Okay, so far we just made a substitution, but nothing happened so far really. Now the magic appears, and it is the core of the renormalization. Okay, so the trick is the following: the trick to eliminate this divergence here, it is the core of the renormalization procedure, consists in redefining the coupling constant E that enters here, there, everywhere, that we will call from now the bare electric charge. So we redefine this quantity here, this constant here, in such a way to exactly absorb the logarithmic divergence of m squared. And once we do this, so essentially we redefine E such that all this quantity becomes finite. And once we do this, we redefine the electric charge, okay? Now we call it the renormalized electron charge, given by this combination, which is now a finite combination, because the divergence of m squared is now absorbed by this new definition of the bare electron charge. So all this quantity, not only it is now finite, but it is exactly corresponds to the measurable electric charge of the electron. This is what we mean by the charge of the electron, 1.6 10 to the minus 19 coulomb. Okay, so let me go again to this this feature, which is essential for understanding the renormalization. So we get a divergence problem. Okay, the first step is to substitute the infinity with the cutoff parameter. We solve the integral. We still have the divergence inside the solution, of course. Nothing really happened from it there. But then we redefine this parameter E, that we will call from now the bare electric charge, which is an arbitrary parameter, as we will see. So we can redefine as we want, and we redefine in the exact way such to absorb completely the logarithm divergence of m squared. So at the end, we obtain a finite quantity here with this redefinition. This we call a renormalized electron charge, and this is the physical measurable charge of the electron. Okay. So once we make this change now, so once you apply renormalization, your matrix element will look like this, okay, where now all quantities are finite. The divergences are gone, are disappeared by construction, because they are absorbed in the definition of an unmeasurable quantity, and the theory is said to be renormalizable. That means it is able to describe physical processes at all orders in the perturbative expansion. Okay, so the problem of the ultraviolet divergence is solved in this way. Now, let me summarize what we have learned in the last 3 slides. So in summary, there is in general a set of bare physical parameters in the theory that are divergent, such as the coupling constant, so the charges, or also the masses, depends on the case, of course. However, these bare parameters are unmeasurable. And this divergent parameter can therefore be chosen or redefined in such a way that they cancel against the ultraviolet infinities coming from the loop diagrams, so from the integral over the loops, the momentum inside the loop. And once this cancellation is operated, we are left with the physical renormalized, or if you like, dressed parameters that are indeed finite and measurable. And in fact, for instance, the renormalized electron charge corresponds to the physical value of the electron charge, which is minus 1.6 10 to the minus 19 coulomb. Okay. Now, as we will see later today, a remarkable result of the renormalization procedure is that the renormalized coupling constant, the electric charge in this case, or if you like alpha, because alpha is proportional to the square of the electric charge, as we've seen, are not actually constant. So the electric charge is not constant, the alpha is not constant, but their value depends on the energy scale. And for the reason this is called a running constant. And the same applies also for the QCD coupling constant, as we will see. So this we will understand better later on. Mi fermo un attimo, è una cosa un po' complicata, ok? Richiede un po' di tempo per essere compresa, ovviamente. Avete domande di sorta prima di andare avanti?
No, per adesso no, grazie.
No, neanche io per un momento, grazie.
Ok, vabbè. Allora, chiaramente diciamo, ribadisco che la rinormalizzazione è una cosa estremamente molto, ma molto più complicata di come ve l'ho raccontata io, ok? Quello che ho mostrato io è un esempio di diagramma divergente di ordine superiore, in cui D, che è il diagramma questo qua, diciamo, in cui compare il loop, okay? Ce ne sono molti altri esempi ovviamente, in realtà a ogni ordine avremo un problema di questo tipo, e quindi ho usato questo esempio per, diciamo, delinearvi le idee di base, okay, della rinormalizzazione, che ripeto è una cosa estremamente più complicata di come ve l'ho spiegata, va bene? A me interessa però che capiate a cosa serve, cosa risolve e quali sono le sue conseguenze. Okay? E come anche può essere in qualche modo testata sperimentalmente, questo lo vedremo adesso nel resto della lezione. Ok, se non ci sono domande, aggiungiamo ancora un'altra particolarità, un'altra feature della rinormalizzazione, che anche questa diciamo, è estremamente importante. Allora, siamo alla slide 8. So, we have seen that the infinities arising in the loop diagram of type A, so so these kind of diagrams here, can be cancelled by a proper redefinition of the electron charge. Now, since the loop regards the photon propagator, so it is the photon that splits into a electron positron and then gets back to a photon, this redefinition of the electric charge is independent of the type of fermion. So it is the same for electron, muons, tauns, or quarks. So here you can have electron, muon, tau, strange quark, whatever you want, okay? And this redefinition of the charge, since it only involves the photon propagator, is the same for all leptons, okay? Which is exactly what we want, because the electric charge of electron, muon, and tau is exactly the same, okay, as we know. However, one can also have diagrams like loop diagrams like this one, where now the loop is here, okay? And in this case, the loop includes the scattered lepton, okay? So now the loop includes also the lepton line here. And so it appears that we should get different redefinitions of the electron charge for different charged leptons. Okay, in principle, one can get different value of the electron charge if you have here an electron or a muon or a tau or a quark pair, whatever. Okay, because now the lepton line is involved into the loop, and this is clearly a problem because we know, for instance, that electron, muon, and tau have exactly the same charge. Okay, same electric charge. However, if one performs a full calculation, finds that there are two additional diagrams, the one that I see here in labeled with C, which exactly cancel the modification introduced in the diagram B. Therefore, if you consider all of them, okay, it turns out that only the vacuum polarization diagram, so the one we showed before, modified the charges, because the modification of the electric charge from this diagram is completely compensated by that originated from these two other diagrams. They completely cancel each other. Okay? So only this diagram here will be responsible for the redefinition of the electron charge. And since it is independent of the lepton you have here, okay, this is absolutely fine, because this is consistent with the fact that the electron charge is the same for electron, muon, and tau. And the same applies for quarks as well. Now, this, let's say, additional magic is called word identity. It is a consequence of the gauge invariance of QED. So this, of course, can be derived formally in the framework of the quantum field theory, okay? And the powerful thing is that it occurs at every order of perturbation theory. So at every order, you can have this kind of cancellation. And so this makes, of course, QED extremely powerful and predictive, okay? Now, renormalizability is a basic requirement of any fundamental gauge theory. A non-renormalizable theory is either wrong, so not physical, or approximated. That means describing some physical process under some approximations, for instance, in some low energy limit, okay? So let me show you here some examples of renormalizable theories and non-renormalizable theories. So in fact, renormalizable theories constitute only a small subset of all possible quantum field theories. And examples of renormalizable quantum field theories are QED, in fact, as we've just studied, massless non-abelian gauge theory, such as QCD, as we will study, spontaneously broken non-abelian gauge theory, as electroweak theory, as we will study as well. Examples of non-renormalizable quantum field theories are the following. Okay, the four Fermion interaction, which was the originally Fermi theory of weak interaction that you probably studied already last year. This is absolutely not normalizable. And in fact, the four Fermion theory of Fermi works pretty well at low energy. So for low energy, weak phenomena, but completely gets wrong when you move to higher energy. And also other examples are massive vector non-abelian theories, quantum gravity, supergravity, which is a field theory that combines the principle of supersymmetry and general relativity. This we will mention in the very last lesson of the course. Okay. So these are either wrong in the sense that they are not physical, or that they can describe correctly physics, but only in some regime. So for instance, a low energy limit or whatever. Okay. They are not universal, whereas only the renormalizable quantum field theories are universal and absolutely correct. So this tells you the importance of renormalization. Okay. Now, renormalization in QED is based, as we've seen, on a proper redefinition of the electron charge. Now, although this may sound as a simple mathematical trick, of course, there is, however, a physical justification for this, and also an experimental way to test this, okay? Several experimental ways. So let's see some examples, okay? So consider an isolated electron here, propagating in time, okay? Each isolated electron can, at a certain point, irradiate and absorb a virtual photon, which in turn can give rise to an E plus E minus loop, okay? This is all virtual, so this can always appear. This will violate energy, but only in the time allowed by the uncertainty principle, okay? So this happens continuously, okay? You have an electron, this happens continuously, and can go, and of course, this radiation can be even more complicated, okay? Now, you can have more loops here, more loops there. The electron or poison can emit a photon, which then further splits and then is reabsorbed. Okay, so this is, of course, the simplest loop diagram you can have. Okay. Now what happens? The original electron then appears surrounded by a cloud of these E plus E minus pairs. Okay, suppose that you have another here, another there. So we have a lot of E plus E minus pairs all around our original electron. But now, due to electrostatic attraction, the positrons, which are positively charged, are of course attracted by the charge of the original electron, so they get closer to the electron, and the virtual electron, so these are the virtual positrons, and the virtual electron as a consequence be farther away from the original electron. So what actually happens is that the vacuum becomes spontaneously polarized. So this is why we call about vacuum polarization, okay? So it's the combination of these vacuum fluctuation, which are all virtual pair creation, together with bare electrostatic attraction and repulsion. Okay. So now let's see what is the consequence of this. Okay. As a result, the positron cloud partially screens the bare charge of the original electron. So we speak about charge screening. Okay. So our electron, which is negatively charged, its charge is partially screened by the presence of this cloud of positively charged particles. So if you want to measure the electron charge by using a probe charge, the result will depend on how deep the probe charge will enter these positron clouds. Okay? If you stay far away, okay, the electron charge is highly screened. If you get inside the cloud, more and more inside, okay, it is less screened, so we will see a higher value of the electron charge. Let's see this in the next slide. So if our probe charge, okay, stays at a large distance from our electron, this corresponds to, of course, a low for momentum transfer because of the uncertainty principle. One observes, the Broglie wavelength. Sorry. So if you have a small momentum, or you get a large distance, and vice versa. So if you are at large distances corresponding to a small low for momentum transfer, then one observes a small electron charge because it is highly screened. You are outside of the cloud. Okay. If, on the other hand, you go to very small distances, okay, so you enter deep into the cloud. So this corresponds to having a high or very high transfer momentum. Then you observe a less screened charge. Okay, so a higher charge. And this you can also represent. So if you put here the effective charge as a function of the distance, you see that as soon as the distance decreases, so as soon as the transfer momentum increases, then also the value of the electron charge rapidly increases, and asymptotically becomes infinite. Okay. Now, all this is about the bare electron charge. So this shows you that if you get infinitely close to your electron charge, to the original electron, you get an infinite value for its bare charge, which is exactly what we used in the renormalization procedure. Okay. We need to introduce an infinitely large electron charge in order to absorb the infinitely large cutoff parameter. And this is exactly what you experimentally can taste if you get as closer as possible to your charge. Now, this is a well-established fact, also from the experimental point of view, and it constitutes, for instance, the explanation of the so-called lamp shift effect that is observed in atomic physics, and that will be discussed in the next 5 minutes. So let's consider the interaction between an electron and the charge of an atomic nucleus, ZER, mediated by the exchange of a virtual photon. Now, due to the vacuum polarization effect, so essentially the diagram that I showed you before, we are talking still about this diagram here. Okay, so we have an electron interacting with an atomic nucleus, and then we have this vacuum polarization effect in between that creates these, at higher orders, you have these clouds of positrons. Okay. So let's get back here. So due to the vacuum polarization effect, the potential felt by the incoming electron is not exactly the Coulomb potential, which is given by this first term here, but includes also a higher order correction that accounts for the E plus E minus loops into the propagator of the extended photon. Or, if you like, they accounts for the vacuum polarization. So let's say the Coulomb potential has to be corrected by an additional factor, or even more factors. You see here, there's a power expansion here that accounts for these corrections arising from the vacuum polarization effect. And so for the effect of these E plus E minus loops. Now, when the transport momentum goes to 0, okay, that means that you are very far away from your original charge of the atomic nucleus in this case. The electron probes the static charge that here ER, where this is the normalized chargeable charge, from a large distance, and thus it interacts only through the Coulomb term. So of course, at large distance, this term becomes completely negligible, and what you see is exactly the Coulomb term that we study in general physics. Okay. When, however, your electron becomes closer and closer to the atomic nucleus, so when the transport momentum increases, it penetrates the cloud of virtually plus minus pairs, which surrounds it, and it does see a larger, or if you like, less screened charge. And this leads to an increase of the effective interaction. In fact, both terms, you see, have the same minus sign. So these terms add up to this one. They don't cancel, they just add. So you add more and more contribution as soon as you get closer and closer to your original atomic nucleus, okay? And so at the end, the effect is like your electron probe is feeding a higher electric charge for the nucleus, okay? And this can be experimentally detected. So it is a not negligible effect that can be observed experimentally. And so this is the lamp shift that we will now discuss. So the measurement was performed using hydrogen atoms, so with Z equal 1. And the correction term, so this correction here, turns out to have a measurable effect on the atomic energy level, and its magnitude can be computed using ordinary perturbation theory in quantum mechanics. So this is the situation. So suppose this is the Bohr atomic level, okay, where you don't even have spin. Then in the Dirac theory, you allow for spin, so you have the first splitting here. And then in QED, you allow also for the vacuum polarization, so you have a further splitting here between the two S1/2 and the two P1/2 levels. And this splitting here is experimentally measurable, and it is exactly due to the vacuum polarization effect. So this splitting here can be calculated in QED, accounting several orders in your expansion, of course, in order to be more precise. And what you obtain from the calculation is exactly what you measure experimentally. So this is, if you want, an experimental proof, a powerful experimental proof, not only of the vacuum polarization, but of QED, okay, in general. So this measurement proves that loop diagrams give rise to real observable effects. And actually, the interpretation of the lamp shift in terms of the vacuum polarization constituted at the time one of the most stringent tests of the theory of quantum electrodynamics. Okay, so it's a pure QED prediction that you have to have the splitting, and then you measure it, and it corresponds. And this rise from, in fact, from these the loop diagrams that you that enter in your power expansion. Okay, so everything is consistent with theory. Let me see. A very important consequence of the Q-square dependence of the electric charge, as we've seen. So the electric charge becomes stronger and stronger as soon as the Q square increases, because you get closer and closer. And so you feel more and more the bare electric charge. So a consequence of this is that also the coupling constant alpha, which is proportional to the square of the electron charge, it also evolves with the form momentum transfer. And so in fact, alpha is not a constant. It is called a running constant or running coupling constant, because its value changes depending on your energy, or more precisely, depending on your form momentum transfer. And let's see how it does change, how it evolves with the scale. So the general dependence of the coupling on the momentum transfer is expressed by the so-called renormalization group equations. Something really complicated, okay? But you see an example here, okay? So the renormalization group equation is something much more general. Let's see now an application here on the case for the alpha electromagnetic. So let me go back here. So the general dependence of the coupling on the momentum transfer, that we call Q square, is expressed by the renormalization group equation, in which the coupling is expanded in powers of the logarithm of Q square divided by mu square, that you see here, where mu is an arbitrary scale, momentum scale. Now, we have a parameter beta z here, beta 0, which depends on the number of degrees of freedom for bosons and fermions in the vacuum polarization terms. And for the case of QED, there are no photon loops. You can only have electron-positron loops, or mu plus, mu minus loops, or whatever, but not with photons. And so it only depends on the fermions degrees of freedom. Now you can invert this equation to get the dependence of alpha on the scale, so on the transferred for momentum. Okay. And so what obtained from this equation here? Okay, so once the coupling constant is known at a certain energy scale mu, suppose you know by an experiment, okay, the value of alpha at a certain value mu, for instance at 10 GeV or whatever, then you can use this equation here to evolve the value of alpha at any desirable value of Q square, 100 GeV, 1 TeV, 100 TeV, whatever you want. Okay. So if you're able to measure precisely the value of alpha at some energy or some momentum transfer, then you can use this evolution equation to evolve the value of alpha, okay, with momentum, with transfer momentum. And it is the essence of the fact that it is a running coupling constant. Okay, it runs with Q square. It is not just a constant. It's not a constant value. We do have, of course, experimental proof also on this, which is in turn again a consequence of renormalization. So the fine structure constant has been determined at very, very small transverse momentum, okay, in atomic physics experiment, and the value is the famous 1/137, okay? But then during the 90s, it was also measured at a much higher energy scale, so order of 90 GeV, which is the mass of the Z0 weak gauge boson. This measurement was performed at the LEP machine, which was an electron-positron collider at CERN, okay, now substituted by the Large Hadron Collider. And the result was that when you measure the alpha at the mass scale, at the scale of the mass of the Z0, you get a larger value. Okay, okay, you have a -1 power here. So this is 1/128 instead of 1/127. Okay, so the difference is not huge. Okay, it is a logarithmic increase, but still you see that how the value increases. And you see that the increase is significant because your uncertainty is only on these last 2 digits here. Okay, and also here. So this proves that the fine structure constants, and so the electron charge at the end, grows slowly with increasing energies, or to better say, with increasing momentum transfer. Can we compare with the experimental data? Yes, again. So this plot I showed you yesterday. So this was about, if you remember, the Baba scattering differential cross-section. This is the angular distribution, so as a function of cosine of theta. The Baba scattering is, if you remember, electron-positron into electron-positron scattering. This measurement was performed at a center of mass energy of order of 200 GeV by the L3 experiment, which was in fact one of the 4 experiments running at the LEP collider, electron-positron collider. Now, yesterday I showed this plot without going to detail, okay? But if If you now look at the details now, you see that we have two curves here. One is the dotted one and corresponds to a constant, so not running value of alpha, which is not able to describe our data, especially in this region here. And the black one is the so-called standard model, okay, where one allows alpha to run accordingly to the renormalization group equation that I showed you before. So the Q-square evolution equation of alpha. And if you allow so, okay, which is of course a major result of QAD, then you are exactly able to match your experimental data. Okay. Another way to show this is to now plot 1 over alpha as a function of Q square, okay? And you see that, of course, this is not flat, it's not a constant, but we have some slope here. And this is, again, matches, again, experimental data from different experiments at different energies. Okay, so the line is the QAD prediction based on the renormalization group equation, and then, of course, the dots are experimental points at different energies from L3 and Opal. Opal was one of the another experiment at the lab. Ok, direi che ci possiamo fermare qui per una pausa. Avete domande, dubbi?
No. Però va tutto bene.
Ok. Ripeto, sono cose diciamo molto complicate che vengono ovviamente studiate in modo corretto e quantitativo in un corso poi di quantitative theory avanzato, un corso di QD avanzato. Noi nel nostro corso ovviamente diciamo, più di questo non vi dico, diciamo, le recite perché sono sempre fondamentali, senza entrare troppo nel dettaglio del calcolo. Va bene, facciamo una pausa, ricominciamo alle 12 allora.
Va bene.
Va bene.
Va bene.
Allora riprendiamo? Mi sentite?
Sì?
Ok. Va bene. Approfitto per ricordare adesso a chi non l'ha ancora fatto appunto di mandarmi quella mail. Trovate il mio indirizzo sulla finestra di chat. Allora, rifacciamo lo sharing del desktop. Ok, adesso dovreste vedere il mio desktop. Allora, completiamo adesso appunto il capitolo della QED con un'altra diciamo, riscontro sperimentale di altissima precisione, ok? Che appunto consente di testare le previsioni della QED a un livello incredibile di precisione, ok? So, precise tests of QED have been performed in many fields of particle physics. We have just discussed about the remarkable case of lamp shift. Okay. Now I will show you another remarkable test of QED, experimental test of QED. Now let me go back to the concept of magnetic moment. Okay, so in general, the magnetic moment is a vector defined as GQ/2ms, where S is the spin vector of the particle, Q is the electric charge, M is the mass, and G is in general the gyromagnetic ratio. Now, for the case of the electron, Q is minus E, M is the mass of the electron, and we can always express the spin vector in terms of de Pauli matrices, as you know from non-relativistic quantum mechanics. Okay. And then you can define the Bohr magneton as EH bar divided by 2 ME. So you put it here. So overall, the magnetic moment for an electron becomes minus G divided by 2, and then the the Bohr magneton times the Pauli matrix. Now, let me also remind you that the Dirac theory predicts the value of the gyromagnetic to be exactly 2. And so in this case, one expects that this ratio cancels, so it goes to 1, and so that the magnetic moment of an electron, where the electron is, of course, a Dirac particle, it is a point-like and spin-off fermion, it is exactly 1 Bohr magneton, okay, because G cancels with the 2 at the denominator. So this is the expectation by the Dirac theory about the magnetic moment of an electron. Now, however, this is only true if you consider leading order processes, okay? But then if you allow for the QED radiative corrections at higher and higher and higher orders, then you see that you have to add the correction to this Dirac prediction, okay? So you see here the ratio between the true value of the electron magnetic moment divided by the Bohr, okay? That means the leading order prediction. So this overall is the QED prediction for this ratio. So this ratio is exactly 1 if you limit yourself to the leading order. Then you go ahead, you have to add a second order term correction, which goes like alpha, a third order, which goes like alpha squared, alpha 6, alpha to the 8, and so on. So as soon as you include more and more diagrams, so you go higher and higher in your perturbative expansion, you have to add corrections, okay, which of course becomes smaller and smaller and smaller because they are dominated by powers of the alpha parameter, which is a small parameter. So overall, okay, the present estimation of this ratio in QED is given by this value here, okay? So it is not 1, it is significantly different than 1. And you see here what precision one can obtain in these calculations, okay? So this is the number of digits, and your uncertainty is only on the last 2 digits. So it is an extremely accurate prediction for QED about the magnetic moment of the electron. Now, how people obtain this precision? Of course, in order to get this, you have to include correction up to higher orders. So up to 8 orders, so all diagrams up to the 8th order, which corresponds to calculating 891 diagrams, plus also the most significant 10th order terms, as well as electroweak and hadronic corrections. So once people, theoreticians of course, have done this incredibly precise calculation, you obtain this value, okay, for the anomalous, let's say, electromagnetic moment. How does this compare with experiments? This is the experimental value, okay? also extremely precise. You see that the uncertainty also from the experimental side is only on the last 2 digits, and you see that essentially these two are the same value. So according to QED, the electron has an anomalous magnetic moment in addition to its Dirac magnetic moment, and the experimental value is extremely close to this precise QED prediction. It's really amazing. You see how many digits you have beyond the point here, and you see that the agreement is incredible up to this point here. Now, there is another way to show this agreement, and also one can also show the prediction and compare with the experiment for the muon case, so the magnetic moment of the muon. So the usual way to represent this is to represent the value of G minus 2 divided by 2. Okay, so you see here the QED prediction and the experimental value. This is for the electron, so what we have just seen in the previous slide, but now in this different notation. And this is the corresponding comparison for the muon. Okay, so first of all, we know that the muon is quite large; it's 3 orders of magnitude larger here, and no, sorry, I think it's the same. No, the order is the same. What you note here essentially is that the agreement is still very, very good, although is a little bit less good than for the electron case. And we will see now the consequence of this, the possible consequence of this. So how was the muon magnetic moment calculation made? So here we get, in this value here, you get contribution from the first order, which is the main one. Second order, which adds a correction. Third order, a smaller correction. Fourth order, a smaller correction. And fifth order, an even smaller correction. When you sum up all these contributions, you get the value which is reported here. And in order to calculate, okay, make this calculation up to the fifth order, people had to calculate the contribution from something like 12,670 diagrams. You see some of them here. So imagine how complicated is this calculation. Now, let's first compare the electron and the muon. Okay. Now, the leading correction term to the 3-level diagrams is the same for electron and muons. So back to the slide before, this term here is the same for both muons and electrons. Whereas the other terms differ. The higher order correction differ for the two, both in magnitude and also in sign, and this is a consequence of the fact that the loop corrections are proportional to the square of the respective masses. And you know that the mass of the muon is order of 200 times larger than the mass of the electron. Okay, the electron is alpha and MeV, and the muon is order of 105 MeV. Okay, and this you have to take to the square. So overall, when you take this ratio, you get a difference of order of 4 order of magnitudes. Okay. Now, why it is so important to look also to the muon? Okay, because the sensitivity to loops involving hypothetical new particles, so particles which are not predicted by the standard model, is much higher for the muon case because of this incremental factor here, a large incremental factor. And so precise measurement of the muon anomalous magnetic moment turns out to be a powerful tool to test the possible existence of physics beyond the standard model. New physics, supersymmetry, dark matter, etc. Okay. So how do you make this? So you have your extremely precise theoretical prediction, okay, which is only based on standard model, so only based on QED. Then you make your measurement, and if you see a significant difference between the experimental measurement and the theory prediction, then this difference could be due to the fact that into the loops that enter in the higher order diagrams, not only standard model objects, but also possibly new particles can contribute to that loop. Okay, for instance, supersymmetric particles. And so this is why searching for the muon magnetic moment is so interesting now, because if you do see a difference, and we do see a small difference here, this might be a first hint of a new physics beyond the standard model. And this is highlighted here. Okay, so consider that now the difference between the two. They are rather similar, but the difference, if you compare the uncertainty, which is very small, the difference is significant. So by adding in quadrature the theoretical and experimental uncertainties for the muon anomalous magnetic moment, one obtains something like 76 10 to the minus 11. Okay, so you're essentially combining these two uncertainties here. But then, if you compare now the values, okay, you find that there is a discrepancy of the order of even larger than 3 times this uncertainty, 3 times sigma, between theoretical and expectation, between theoretical expectation and experimental value. And of course, this discrepancy has triggered a wide debate in physics community. We call this the G-2 problem. Okay, we have a problem. We cannot interpret our result completely within the standard model. We probably need to go beyond this. So in fact, this is still a question. It's not sure. Okay, so does this discrepancy arise from the still limited accuracy of the theoretical calculation? So maybe you would attain a slightly different value if you would include higher and higher order in the calculation, 6th order, 7th order, and so on. Or it is indeed a first evidence of a new physics beyond the standard model. At the moment, we are in the question mark status. We don't know, okay? Including the theoretical, the precision of the theoretical calculation is extremely challenging because we have to go really to calculate thousands and thousands of new diagrams. On the other hand, we can also try to improve the precision of the experimental measurement, and a new experimental data with an improved precision by a factor of 4 are expected to come in the next year. So, okay, this year everything will be shut down because of the COVID, but hopefully in the next years. From the E989 experiment at the Fermilab. Fermilab is, you know, is a particle physics laboratory close to Chicago. It is the place where, for instance, the top quark was discovered in the 90s. Okay. So this is a working process. Okay, we have some hint of new physics. We don't know. Is maybe just because our theoretical calculation is not precise enough. So we'll see in the next year if something new comes from this sector. Ok, se ci sono domande su questa parte, altrimenti andiamo avanti e cambiamo argomento.
No domande?
No domande?
No, per me non ci sono.
Ok. Va bene. Allora, adesso con questo chiudiamo il capitolo della QED. Ok? E andiamo adesso avanti con il corso. E il capitolo successivo, che corrisponde al modulo 4, riguarda spin statistics e soprattutto discrete symmetries. Ok? Quindi lo inizieremo oggi, questo capitolo qui, e poi te lo porteremo a termine la settimana prossima. Allora, cominciamo con, sono delle cose che probabilmente, anche queste, quasi tutte avete già fatto nei corsi di meccanica quantistica l'anno scorso. Okay? In ogni caso, insomma, per me è bene richiamarle perché ci serviranno poi appunto per introdurre il concetto di parità, calcolarla e così via, okay? Per vari sistemi di particelle. Ok, cominciamo con qualcosa che sicuramente conoscete bene, the spin statistics. So all particles, either elementary particles or not elementary particles, such as the proton, the neutron, etc., can be categorized into two groups according to their spin, and so according to their statistics, essentially, the statistics that they follow. So fermions, they have half integer spin, 1/2, 3/2, 5/2, and so on. They follow the Fermi statistic, the Fermi-Dirac statistics. So they follow, of course, for instance, the Pauli exclusion principle, which is a consequence of the Fermi-Dirac statistics. And as you know from quantum mechanics, the total wave function must be antisymmetric for exchange of any two identical fermions. What about bosons? Bosons come with integer spin, 0, 1, 2, etc. They follow the Bose-Einstein statistics, so they also can produce Bose condensates, where many thousands, millions of bosons can condensate in a single quantum state. And as you know, the total wave function must be symmetric for the exchange of identical bosons. So let me now switch to the blackboard or the whiteboard. Okay. Ok, vedete la lavagna bianca?
Affermativo.
Sì.
Bene, a posto. Allora, spero di averlo orientato correttamente. Facciamo una prova, vediamo se è vero. Sì, ok. So let's consider a system of two identical particles. One and two, which are described by a total wave function psi 1, 2. So this is a two-particle wave function, where 1 and 2 are two identical particles in general. Okay, and let me now introduce the exchange operator. We call it I, capital I. And it is such that when you apply the exchange operator to your wave function, it just changes the two particles. So apply to 1, 2 provides you 2, 1. Okay. Now, obviously, we expect that if we apply the exchange operator twice, we expect that we get back to the original state. So suppose we have I squared psi 1, 2. This we can split into I, and then I psi 1, 2. That is I. Now we make the change here. So this is going to be psi 2, 1. And then we have to exchange again. So this comes back to psi 1, 2. Okay. So overall, we have that an eigenvalue equation of the operator I squared. So I squared psi 1, 2 gives you plus 1 psi 1, 2. Okay. This term gives you this term here. And this means that so the eigenvalue of I is 1, and so the eigenvalue of I squared, the eigenvalue of I, sorry, this is not an operator, it's eigenvalue, can be plus or minus 1. Okay? That means that in general you can write the eigenvalue equation for the exchange operator, psi 1, 2, as in general plus or minus 1 psi 2, 1. Okay? Now, let's consider the case of two identical bosons. So the wave function of a system of two identical bosons, of course, is symmetric under exchange of the two bosons. Okay, so we know that we must have psi 1, 2 has to be equal to psi 2, 1 because they are bosons. Okay, so when we apply now the exchange operator to psi 1, 2, is going to be psi 2, 1, which is equal to psi 1, 2 because they are bosons. And so this comes with the plus 1 eigenvalue. So for bosons, the eigenvalue is plus 1. Let's now repeat the exercise with two identical fermions. So we know that in this case, the wave function is antisymmetric. So psi 1, 2 is equal to minus psi 2, 1. And so when we apply the exchange operator, psi 1, 2, this gives you psi 2, 1, which is equal to minus psi 1, 2. That is minus 1 psi 1, 2. So we obtain here an eigenvalue equation for the case of fermion, where now the eigenvalue for the fermion is minus 1. Okay? Now, as you know, in general, the total wave function can be factorized into a spatial term and a spin term. Sorry, I have to change now board. Okay, so this is now page 2. So you know that in total, the total wave function C tot, you can always split into a spatial times a spin wave function. This we can write better as psi r for the spatial term, and let's introduce the chi wave function for the spin component only. Okay, now the spatial part, as you know from quantum mechanics, we can represent in polar coordinates, so as r theta phi, that is phi r, and then you have your angular dependence expressed in terms of the spherical harmonics, m theta phi. And so, as you probably remember, this is proportional to, so this is, let's call this psi r times, now we have your full expression of the spherical harmonics, which is in general 2L plus 1, L minus m factorial, divided by 4 pi L plus m factorial. Then you have your Legendre polynomials, which are function of cos theta. And then you have this phase, e to the e m phi. Okay, so far nothing new. This you know already from quantum mechanics. Now, the exchange of particles, so 1 into 2 and vice versa, corresponding to the inversion of the spatial coordinates. So this corresponds to changing r into minus r. And when you now represent these in polar coordinates, this corresponds to changing theta prime as pi minus theta, phi prime as pi plus phi, and r prime remains untouched. That means that for the radial component of the wave function, there is no difference. This remains the same. What about now the angular part of the wave function, so the spherical harmonics? How do they change when we swap their spatial coordinates from r to minus r? So when we apply this transformation on the angles. So we start here from the transformed spherical harmonics, theta prime, phi prime. This is proportional to the Legendre polynomial of cosine of theta prime times e to the minus I m f prime. Now we substitute. So we have the Legendre polynomial for the cosine of phi minus theta. And then we have e to the I m phi plus phi. Now, it turns out that when you transform the polynomial in this way, so the argument of the polynomial, you get a factor -1 of L plus m to the L plus m, and then you have now the untransformed polynomial, cosine theta. And this you can write as e to the I m phi times e to the I m phi. Now, let me make a detour here. So e to the I m pi, you can always write as cosine of pi m plus I sine of pi m, where m is an integer. That means that the sine is always 0. Okay, is 1 pi, 2 pi, 3 pi, so the sine goes to 0. And so, and the cos, when you change the argument from 1, 2, 3, 4 pi's, the cosine just becomes a factor of -1 to the m. -1, +1, -1, +1, etc. So here, when we are now back to our spherical harmonics, we're going to have -1 to the L plus m plus another m that comes from here. One m here, okay, and the other m is there. So we have 2m Then we have the untransformed Legendre polynomial. Then we have e to the I m phi, which is the last term remaining. Now, the effect of the 2m here, of course, is irrelevant. Whatever number is m, 1, 2, 3, 4, 5, either even number or an odd number, when you multiply by 2 is an odd number, is an even number, sorry. So it makes no difference in the value of this coefficient here. And so this is absolutely equivalent to minus 1 to the L. And then you have your ordinary spherical harmonics left. Okay. Here I put a sign of proportionality because we are for the moment forgetting about all these coefficients we don't care about. Okay, so what we need is to see how the spherical harmonics and how these two terms changes when we swap the spatial coordinates. Okay, so the overall effect is that the radial component remain unchanged. Okay, so psi r prime is equal to psi r, but your spherical harmonics gets an additional factor of minus 1 to the L. So now we can put everything together, and we see that if we apply our exchange operator to the spatial component of the wave function, that is psi of r prime, we're simply going to have minus 1 to the L and then the untransformed wave function. So the effect of this exchange operator is to add this minus 1 to the L coefficient. Sorry. And this is what we get when we swap particle 1 with particle 2. So our beginning was here. Okay. So when we swap particle 1 to particle 2, our spatial wave function gets this additional factor minus 1 to the L. Let's move on. So to summarize, what is the value that one obtains? So the symmetry, let's say the symmetry of the spatial component of the wave function is given by minus 1 to the L. And so if L is an even number, then it turns out that the spatial is symmetric because you get just a factor of 1. If L is odd, then your spatial wave function is antisymmetric. So this was for the spatial component of the total wave function. Let's now see what happened to the spin component. Okay, so we are talking about now a system of two identical, let's consider fermions first, okay? So fermions. So we have a system of two identical, let's consider a spin 1/2 fermions, okay? Now, as you remember from quantum mechanics, the spin of two fermions can be parallel or antiparallel and can be combined in 4 different ways to form a singlet and a triplet state. So for the singlet state, this corresponds to S equals 0, and so also Z component equals 0. And the wave function, the spin wave function from 0, 0 is of the form 1 over square root of 2, and then you have spin up for the first particle and spin down for the second particle minus spin down for the first particle and spin up for the second particle. For the triplet case, in triplet state, one has instead S equal 1, and therefore SZ can take three values, +1, 0, and -1. And this corresponds to the following wave function sub psi 1, 2, 1, 1 is equal to both, of course, spin up. The psi 1, 2, 1, -1 corresponds to both particles with spin down. And then we have the mixed term, the psi 1, 2, 1, 0, which is the combination 1 of square root of 2, spin up for 1, spin down for 2, plus spin down for 1, spin up for 2. Now, what about now the symmetry of these states? Okay, so let's start from the singlet state. So the chi 2, 1, 0, 0, we obtain applying the exchange operator to the chi 1, 2, 0, 0. That is 1 over square root of 2. So now we exchange 2 with 1. So this is spin up for the particle 2 and spin down for the particle 1 minus spin down for the particle 2 and spin up for the particle 1. Now you just swap these, which makes no difference in the wave function. So this you can just rewrite is absolutely equivalent to spin 1 down, spin up for the particle 2 minus spin up for the particle 1 and spin down for the particle 2. And now this is exactly minus 1 over square root of 2 of spin up for particle 1, spin down for particle 2, minus spin 1 for particle 2, particle 1, spin up for particle 2. That is minus chi 1, 2, 0, 0. So the chi 2, 1, 0, 0 is equal to minus chi 1, 2, 0, 0. And so the singlet state is antisymmetric. On the contrary, it turns out that the singlet state is a symmetric one. So let me now change the page. So now for the triplet state, one finds that using the same trick as before, so applying the exchange operator, one eventually finds that psi 2, 1, 1, 1 is equal to psi 1, 2, 1, 1, psi 2, 1, 1, 0 is equal to psi 1, 2, 1, 0, and sorry, chi 2, 1, 1 minus 1 is equal to chi 1, 2, 1 minus 1. So the triplet state is symmetric under exchange of 1 with 2, particle 1 with particle 2. So how can we generalize this, okay, for any value of the spin, okay? So the symmetry of the spin component for fermions is given by -1 to S plus 1. In fact, we see that if S is even, that means 0, 2, 4, etc., then you get a minus sign here overall, okay? And so your spin component of your wave function is antisymmetric. can call it psi A to say antisymmetric for the spin. If, on the other hand, S is an odd number, like for the triplet, spin 1 or 3 or 5 or whatever, then the spin component, so we get an overall +1 factor on top of this, so the spin component is symmetric. So we call psi S to say symmetric for the spin component. What about now bosons? Okay, now for bosons, the state with total even spin are symmetric, while those with total odd spin are antisymmetric. So they are exactly the opposite. So for bosons, let's consider the simple case of spin 1 bosons, for instance. Suppose that we have spin 1, so an odd number. So we have 3 projection. Let me see, one moment. No, sorry, it's two spin 1 bosons. Okay, of course. We're talking about system of 2 particles. So 2 spin 1 bosons. Then one have the following combination. So S equals 0 turns out to be symmetric. S equal 1 turns out to be antisymmetric. S equal 2 turns out to be again symmetric, etc. So how can we generalize now the symmetry of the spin component of the wave function for bosons? Then we have the following: -1 to the S. And in fact, if now S is even, then 0, 2, 4, etc., then the spin component is symmetric in this case. So it's just the opposite. And so we get the psi S spin, whereas when the value of the spin is odd, so 1, 3, 5, etc., then the spin component of the wave function is antisymmetric. So psi A spin. Okay, so this gives you the symmetry of the spin component for fermions. This gives you the spin of the spin component for bosons. And in the slide before, we've seen the symmetry of the spatial component of the wave function. So we can now combine all together everything. We go back to the slide. So we know that the wave function for the fermions must be, the total wave function must be antisymmetric for exchange of 2 identical fermions. So this is the symmetry of the spatial part, as we've seen. This is the symmetry of the spin component, as we have seen. So we can combine them to get -1 to L plus S plus 1. Okay. Now we impose that this coefficient must be -1 because we want the wave function of 2 identical fermions to be antisymmetric. And so this is only possible when L plus L is an even number. On the other hand, for bosons, we want the wave function of 2 identical bosons to be symmetric. So this is the symmetry of the spatial part, which is the same. This is the symmetry of the spin component, which is different, as we have seen, is opposite. So we combine them, we get -1 L plus S. We enforce this coefficient to be +1 because we want the wave function to be symmetric for exchange of identical bosons. And again, this is only possible when L plus N is even. So let's see now what happened for fermions. So overall, we want the wave function to be antisymmetric. And you can obtain this by multiplying an antisymmetric spatial component with a symmetric spin component, or vice versa, a symmetric spatial component with an antisymmetric spin component. So the spatial component is antisymmetric if L is odd. The spin component is symmetric when S is odd. Okay, and so when you add up 2 odd numbers, you get again an even number. So this is exactly what we wanted: L plus S equal to an even number. And this is the same here. So in order to get a symmetric spatial wave function, you want to have L to be even. And an anti-symmetric spin wave function, you want to have S to be even. Now we are adding up two even numbers, which again gives you an even number. So the first condition here is fulfilled. Let's now see for the bosons. Now for the bosons, you overall want to have a symmetric wave function. So the only possibilities are combining a symmetric spatial component with a symmetric spin component, or an anti-symmetric spatial component with an anti-symmetric spin component. Okay. Again, you apply the rule we have just seen before. So in this case, you're going to have L even and S even, and the sum is again L plus S even. And in this case, you have L odd and S odd, but again, the sum of two odd numbers give you an even number. So also this condition here is fulfilled. Ok, per oggi ci fermiamo qui. Avete domande su questa parte?
Io no.
Ok, sono cose che in grossa parte sicuramente avete già trattato in meccanica quantistica. Esatto, ok, quindi diciamo adesso quello che faremo la prossima volta è utilizzare questo risultato per introdurre le simmetrie discrete, quindi parità, polarizzazione di carica, time reversal, e entrare in gioco quello che abbiamo spiegato anche oggi. Va bene, se non ci sono domande noi ci vediamo quindi mercoledì alle 9. Chiedo a chi non l'ha ancora fatto di mandarmi la mail. Basta. Buon weekend a tutti.
Altrettanto, professore.
Buon weekend.
Grazie altrettanto, arrivederci.
Arrivederci.